Okay, so I will start anyway. So the point of this 1 hour, maybe slightly more session, is to give you the latest updates on SpeechBrain and the roadmap as well, where we want to go. So the idea here is that we will be multiple speakers presenting different things, so that you get a better view of what is new in SpeechBrain. And so to start, I think what is important to remember is that it took us 3.5 years of development, but SpeechBrain version 1 is here, almost here. It will be soon deployed. And so this is it, right? We won't be in beta anymore. This is like, I think, the biggest news for us. With so a lot of functionality that we will discuss, but that's the main point here. SpeechBrain version 1 is here. And so why version 1? Because looking at the different issues and GitHub statistics, we think, at least the core team members, they think that SpeechBrain is no stable. And if you just look at the statistics as well, well, that's more than 150,000 PyPy downloads every month. So we also think that the toolkit is being used, apparently. And also, well, all the initial core team members have basically implemented all the features, almost all the features that we originally planned to implement in the toolkit. This combined with the fact that the community is using the tool and also thinks that SpeechBrain is a mature tool, we are quite confident to say it's time now to finish everything, freeze a bit, and say that this is SpeechBrain version 1.0. I would like also to mention briefly that for the very first time, we are introducing a few minor changes that will not be backward compatible. But don't panic, everything will be explained, and usually it's very small, like a few lines change in your YAML or in your recipe. So what is the SpeechBrain version 1? Well, that's more than 70 merged pull requests since the last version. That's a total of 130 contributors, and that's a total of 190 training recipes. So there are a lot of statistics that can be also extracted, but let's stick with these ones. And we will also promise to not go above 150 open issues. And this is quite hard because we don't have any bot, right? We're not stalling issues on things. We are actually addressing issues when we have enough time to do it. So we won't go above 150. And this has already been the case for the past year, if you look at the statistics. We also have more than 200 people on Discord. Feel free to join and come and chat with us. And initially, SpeechBrain version 1 will be available on the develop branch only. So this means that you will need to install SpeechBrain from the GitHub sources. This is simply because it's a huge step forward, and we first need to see if everything is working properly, if the community is happy with this new version before actually putting this into the master branch of SpeechBrain so that you can install it with PyPy. But it should be quite quickly done after this first step. So as I said here, the idea is that we will first have a brief overview of what is new, and then every single topic of interest that we think is of interest will be presented by the real human beings behind the innovation, behind the pull request. So for the brief overview, there will be a lot of new things on automatic speech recognition. Of course, we have better models now, conformer, hyperconformer, branch former, better transducers, maybe some former that will come as well very soon. We have more data set, rescue speech, AMI, Tedium 2 that is also ready to join. We have now the foundations for streaming ASR based on the conformer transducer. This is also PR that will be merged very soon for SpeechBrain version 1. And we have K2 powered lexicon constrained decoding. And I think the most important point is the complete refactoring and enhancement of the ASR decoding pipeline. Adele will tell you more about this, but basically if you want a simple example, for instance, and that's just a very small example, well, now it's feasible to rescore or use shallow fusion with, let's say, a UBERT-based ASR system and using a GPT language model from Hugging Face, for instance. This is not feasible. We also have SpeechBrain benchmarks. That is a new SpeechBrain repository, and I won't say more on it because it will be introduced in details. But basically, what we thought is a recipe-based directory tree isn't really adapted to multitask benchmark, right? Right now, we have this recipe folder where you have LibreSpeech and so on and so forth. And so this means that you have always the best model for each data set. But this is not aligned with, let's say, I don't know, if you think of Superb for SSL, or if you think of other benchmarks where you have very specific ways of evaluating your models, right? Well, this is why we introduced SpeechBrain benchmarks. That is a separated element, and more on this later as well. Voice and speech synthesis. We now have fast speech too, both training and inference. We also have the DeepWave vocoder that is ready to join the party. And we have now examples of training zero-shot TTS systems. Speech-to-speech translation. We are introducing in SpeechBrain the first recipe to train a speech-to-speech translation system. So translating directly from the speech to the speech without going in the middle with the text. And this will be based on discrete units and the idea that was developed by Meta on textless speech-to-speech translation. So this, of course, introduces also recipes on specific dataset like LG Speech and CVSS. More on this later again. We also have a complete refactoring of the Hugging Face Transformer interface. Up until now, SpeechBrain was limited to Whisper, UBERT, WaveLM, and Wave2Wave 2.0. So basically any interface that we, the core team, was providing to you. Otherwise, you had to do your own custom class on your side if you wanted to use more. Now you can load any transformer model coming from Hugging Face, any of them, right? You will only have to inherit from a few functions. Everything will be explained, tutorials. It's very simple, but this means that you can just use anything coming from the transformer library of Hugging Face and put this into SpeechBrain. Well, yeah, by the way, this is one of the part breaking the backward compatibility. But again, do not panic. It's just a one-line change in your YAML usually. So everything is fine, hopefully. Then, of course, continuous integration, because we know that it matters for our users. All our recipes are entirely automatically tested with one or multiple GPUs, right? So all the recipes that you are using, they have been tested, not for the final performance, but at least to see if everything runs properly. All the Hugging Face interfaces are also automatically verified. We improved integration and unitary tests to cover most SpeechBrain functionalities. And if you are interested by this topic and how it's done in SpeechBrain, please jump into the test folder, because we just enhanced the documentation by quite a lot. And so it's like almost a completely different repository inside a repository, if you're interested by this, to see all the different tests that we are doing and what is the zen and ideas behind our testing methodology in SpeechBrain. And of course, we hope that our audience understand that it's not because we are testing that there aren't any bugs, right? We are testing because bugs are actually here. Please raise issues if you find one, and we'll try to fix it. And also much more features as well that will be detailed a bit more later, or well, that we won't have time to detail maybe for some, but at least is here basically. So we have like a new interpretability recipe. We have GPT-2 fine-tuning. We have diffusion models, some new speaker recognition models, new speech enhancement recipes, new emotional recognition dataset and recipes. We have now brain EEG processing. So we have a new recipe for this. We also have an example of a Bayesian ASR model and more streaming features. Of course, SpeechBrain version 1 will feature a lot of bug fixing, which are part of the 7 TPRs that we have. And very importantly, I can say that we are supporting PyTorch 2.0, 99% of the functionalities of it, which doesn't mean that you won't have any bugs while trying to move to PyTorch 2.0, but at least most of SpeechBrain is now compatible with PyTorch 2.0. So you can use it straight away, starting from SpeechBrain version 1.0. And with this being said, I will just hand over to Adele that will present in details what are the news for the automatic speech recognition.
Maybe we can remark that if you guys have like some questions, you can use the chat, and we are here to reply. Okay, so do not hesitate to ask questions in the chat. We are here to help. Okay, go ahead.
Okay, do you see my screen?
Yeah.
Okay. So first, I'm really pleased to be here, and I'm also really pleased to see so many people attending our SpeechBrain online summit. My name is Adel Moumen. I'm a master student, and I've been working on SpeechBrain for over 1 year. And today I'll be talking about some of our latest features regarding automatic speech recognitions, but more precisely on the decoding pipeline of ASR models. So let's get started. This is, as you can see on the screen, this is a mind map showing all of the different manners to decode a model, an ASR model. This has been built on the latest papers coming from the literature. And every item that is crossed is what we are currently supporting in SpeechBrain. And what you can see is that we are lacking for a lot of different manner of decoding ASR models. We're lacking from some features. For instance, on CTC joint attention, we are missing a way to rescore with n-grams, and also the interface is not quite, it's not intuitive, it's not modular enough. On the CTC part of thing, we do not have ways to decode with a pure CTC or use like WSSTs and so on. And we are also like missing from large language model rescoring. And today I'll be really focusing on the three manners of decoding. So we are introducing a new way, a new joint CTC attention decoding interface. So as I said, our current interface in SpeechBrain 0.5 was not modular enough. It was very hard to understand, modify, mainly because the search part and the rescoring part were combined together. So if you wanted just to modify the rescoring part, you had to also understand the search part, and sometimes you can mess up, when you try to modify the rescoring part. So it was hard, for instance, to add new score like n-grams language model. And also it was impossible to perform pure CTC decoding with the CTC joint attention decoding. And this is really where the new interface is taking place. It's more modular, easier to understand because we made sure that both parts are separated. So there is a distinct search part and a rescoring part. Adding new scorers have never been so easy because we were able to introduce n-gram language model in easier manner. And it is also possible to perform pure CTC threading and decoding. So I will just show you an example. This is two YAML files in SpeechBrain for a sequence-to-sequence recurrent neural networks with on the left a beam search, a language model, RNN language model, and on the right a transformer language model. And as you can see, for each kind of language model, you had to redefine a new interface that will work out the box with the language model. And this is an issue because if now we want to just use the beam search without the language model, you had to directly change the interface, the Python interface. And if now we wanted to, use a different transform language model or like an n-gram language model, you had to redefine another interface. And this is not scalable. Also, it is also applied for other beam search. Just take like a sequence-to-sequence transformer. It is also the same issue. So the new beam search interface in SpeechBrain 1.0 is still supporting batch and GPU decoding. This is a vectorized beam search, simplified and easier to read. And one key point is the separation of the scoring part from the search part. There is now two distinct objects, scorer builder and sequence-to-sequence beam searcher. Basically, the sequence-to-sequence beam searcher is a new class that is handling the search part. You don't have to really define it. It's already provided to you. And there is a scorer builder, which basically is handling the scoring part. And and also like as a new features, we are providing like n-gram language model rescoring. We also give the possibility to score either partial or full candidates, where partial means you only select the top K candidate, so you can only rescore on this subset, and can be great to lead some speed up. And it also this new PIA, this new interface sets the foundation of neural language model rescoring. So in SpeechBrain 1.0, if you want to use a recurrent neural network language model with a sec-to-sec RNN, on the left, so on the figure 4, you can see the new version. So the first part is you have to define your scorers. So in this case, you are defining a coverage scorer and a RNN language model scorer. Then you have your score builder, which is handling the scorers, and you have to specify the weights for each scorer. And then you add your score object in your beam search, and that's it. And what is really great, as you can see, is that if you want to remove the RNN language model scorer, you just have to remove it, and you don't have to switch to fall back to a new interface and so on. And you can even like trigger multiple scorers if you want to add like a transformer language model scorer, an RNN language model scorer, and so on. You can trigger everything in the same class. The only drawback with this new interface is that it is backward incompatible. But we are releasing a Google Colab tutorial, which will cover everything and will be released shortly so that you are not lost. And we really hope that this new interface will be easier to use, and you will be able like to develop in an easier manner new language model scorers and so on. And like one problem with this interface, this CTC joint attention interface, is that when you are doing pure CTC decoding, the issue is that it is very slow, not because of our implementation, but because of the theoretical background of the implementation of CTC joint attention. And as I demonstrated in the mind map, we were lacking from pure CTC decoding, and that is why I'm really pleased today to introduce new ways of doing pure CTC frame synchronous decoding. The main advantages of our new interfaces is that they are very fast and easy to modify. We support a lot of heuristics to make them very fast, and everything in Python so that you can modify it very easily. It supports n-gram rescoring with KNLM integration, works out of the box with different type of tokenization for your acoustic model, such as sentence piece or only characters. And we release 4 different CTC beam searcher. The first one being CTC beam searcher, which is just a vanilla beam search, which is not taking care of blank and non-blank probabilities, while the CTC prefix beam searcher is following a paper that we are citing in the docstring, and that support like blank probabilities and non-blank probabilities. And both of them are supporting n-gram rescoring, and they are really fast. I will show you just in one slide some of our results. And finally, we are supporting Torch Audio wrappers. So Torch Audio is a toolkit provided by the PyTorch team, and they release a CTC prefix beam search in C++ for CPU version and in GPU. And it supports like n-gram rescoring, a constraint search, and it's really great. And we propose a new wrapper so that it is compatible out of the box with SpeechBrain model. And you can, for instance, with the GPU version, decode HL dataset, test a dataset in like 5 minutes against like 20 minutes, which is kind of fast. And in terms of results, as you can see on the table, this is a result of a fine-tuned wave-to-vec2 on LibreSpeech datasets with a different CTC beam searcher. All of the results are computed using the same exact system with a batch size of 1 and more than 143 beams. Our baseline is a greedy search, and you can see that our new implementation are quite competitive. We can, with the CTC beam search with 4 gram LM trained on LibreSpeech, we can reach 1.75% of water weight in about like decoding the test clean in about like 2 minutes and a half, and a little bit more than half. And this is really fast, and this is quite the same as the greedy search, but we are able to down the test clean water weight by a lot. So moving on to another point of the mind map, LLM rescoring. We are introducing neural language model rescoring. So what is neural LLM rescoring? basically, it's like a language model that has to re-rank the candidates produced by the beam search decoding. So an LM, a language model, it gives a score to each candidates, and then we combine the score with the acoustic model score, and it produces a final ranking. And what is really great with a neural LM rescoring is that you don't have to make sure that your ASR model and your language model share the same tokenization, because it directly works on the raw text of the candidates. So you don't have to fully retrain your acoustic model or your neural language model. And you can, like, it is working with the Hugging Face auto model for causal LM. So you can take any language model from the Hugging Face hub. It could be either like a large language model or just a simple language model, such as GPT-2 if you want to use a large one. It is really fast, as it is only applied at the end of the beam search, and it is compatible with all of our beam search, such as the transducer beam search, pure CTC beam search, CTC, the joint attenuation beam search, and so on. And it gives competitive results when you combine, for instance, a wave-to-wave model plus the previous CTC beam search and a transform language model trained on LibreSpeech. You can down the result to 1.62% of order rate on the test clean and 39% on the test order of LibreSpeech, which demonstrates the effectiveness of using this new language model. And finally, one really great news is K2 decoding in SpeechBrain. Finally, K2 is a new toolkit that integrates finished state automaton, FSA, and finished state transducer into PyTorch. This is led by the Caldi team for the next-gen Caldi toolkits, and it integrates like various training objectives such as cross-entropy, CTC, and MMI. And basically, it jointly optimizes the ASR system with multiple decoding passes, and also it provides like confidence estimation and so on, and also like support of constraint lexicon, n-gram rescoring, and more. And this is very great because it is solving some of our issues that we were lacking from WSFSTs and so on. What is our current integration of K2 in SpeechBrain? Currently, we are supporting K2 CTC training and lexicon decoding. We obtain competitive results with way-to-wake, achieving like 1.83% of water rates. And we have some ongoing work on the integration of K2 HLJ and n-gram rescoring, as well as some ongoing work on speech alignment with K2. And we really hope that you will enjoy using K2 plus SpeechBrain for your recipes. I'd like just to thanks all of the people that contributed to all of these new ASR decoding features. And if you have any question, please let me know. And thanks everyone.
Thank you, Adele. I think maybe it's a good moment for questions, right? So feel free to write in the chat while we change speaker. I think that this is pretty remarkable achievement. Now we have like many more options for search, which make, I think, the toolkit pretty complete from that point of view. And I'm wondering if from the audience there are questions or curiosity about what we are doing here, or even suggestions. So maybe people are like thinking about that. Meanwhile, maybe let me. Oh yeah, there is a question here, right? Are there any plans to distribute SpeechBrain via Conda Forge? Okay, that's maybe not related to decoding, but maybe Adele, if you, or Titwan, if you had some plans.
I don't know, but I think like it could be valuable to have SpeechBrain on Conda as well. I will write on my paper about that. But yeah, I think it could make sense to support like SpeechBrain via Conda or Conda Forge.
So Titwan, what do you think about that?
You will have to clearly identify why people wanted to see SpeechBrain and Conda. Because if it's a matter of having something that install everything properly, so you get a proper environment, meaning that it is maybe aimed at production, maybe providing some Docker image will be better in this case. So we just have to understand why there is a need for this, I think.
Yeah. Is there any other question? Okay, let me share. Maybe you have other questions. Maybe meanwhile, let me share my screen. Okay. So I hope hello, can you see my screen?
Yes.
Yep.
Okay. If there are no more questions, no problem. Just write the question in the chat, if any. Oh, looks like so there are some questions. Yeah, maybe there is a question about from Yannick for you, Adele. In your experiments with K2 SpeechBrain, did you optimize the FSA weight by applying the K2 capabilities that make these weights differentiable?
I'm not the one that is working actively on the K2 integration, but if you want, I can give you the contacts of the authors of the paper. There's still some ongoing work, like we still have to review and clearly understand everything. But I can't answer the question like that.
Yeah,
sorry.
maybe Zayu is here, maybe he can reply in the chat. And see. But I think, yeah, I think so, because yeah, they are using like Caldia for training purposes as well. So maybe that could be the case. Okay. See, there are other questions. Oh, Zayu, maybe Zayu, can we switch on the microphone, right? To Zayu for replying this question about K2.
We cannot talk currently.
I cannot unmute it. Okay.
I just gave.
We need to give
Hi,
the
can you
words.
hear me now?
Yep.
Yeah.
Yep.
Okay,
Yeah,
okay.
please.
Now I can mute it. I just didn't have the right to say anything.
Feel free to reply.
Okay, so I saw there's a question about, so in your experiment with K2 or SpeechBrain, did you optimize the FSA weight by applying the K2 capabilities that makes these weights differentiable? So basically, K2 is a differentiable diversity framework, and so during the training, we just used the K2 to construct the training graph and combine it with the output of the neural network, and then just do the training. So the K2, the training graph will be used as a filter, and the output of the neural network will be transformed into animation FST, which is a kind of a dense FST. So for example, if you have T time steps, we will have like T+1 states in the resulting emission FST. And from one state to another state to the next representing the next time step, there will be exactly the same number of transitions, which is the same as the number of the possible tokens we have. And so, and the transitions and the weights on these transitions actually are picked from the output of the neural network. Yeah, so that's how we optimize it. So and we use the K2 to calculate the loss function, for example, like CTC loss function, and the loss, and the K2 will help us to calculate the gradients automatically and back propagate it to the log probabilities, which is the output of a neural network, and then back propagate to the whole neural network to update the parameters there. I'm not sure if I just answered your questions.
Yeah, maybe you can follow up in the chat if needed. Thank you very much, Zayu.
No problem.
We can move on. So yeah, beyond like the search part, the coding part, search part, there are many other news, and one pretty exciting is the creation of the so-called SpeechBrain benchmarks. What is that? You know, SpeechBrain benchmarks are like actually a new repository created under the SpeechBrain one. And you know, benchmarks are essentially a bunch of recipes that are created to measure the performance of a model or of a technique. Like, and this will allow user like to experiment different models or techniques in a kind of standardized setting where you know, the results are hopefully comparable. So we work hard for a few benchmarks, and there might be many more in the futures. Currently, the SpeechBrain benchmarks include these three benchmarks. One is called CL Maser, which is like pretty cool because it can be used to evaluate continual learning techniques. Specifically here, the task is like continual learning of new languages for speech recognition. With that benchmark, we also implemented a bunch of continual learning techniques that can make our toolkit suitable for research on continual learning as well. So that's a pretty big leap. And then Luca, who is here, will describe better this benchmark. The second benchmark that we are pretty proud to host is the MP3S one, which is the design for a fair assessment of self-supervised speech representations. Like there was a paper like at InterSpeech like last week mentioning that, and Salah will tell some more details about that. The third one, which will be soon available, is actually benchmark for the assessment of neural networks for EEG tasks like motor imagery, P300, and SSVP. So as you can see, like SpeechBrain is like started as a speech processing toolkit, but now it involves also language, text, and why not? You can really extend it to EEG processing as well. As far as you have a sequence to process, I think SpeechBrain can be considered for that. And we are actually, we work very hard to, design this EEG benchmark called SBMOR. But I would like maybe to leave Luca describing the first benchmark, the one on continual learning for new languages. Luca, are you there?
I just gave voice access.
You don't hear me?
Yeah, go ahead, Luca.
Okay, let me share my screen.
No, I can like you can
Okay.
just
Yeah, sure. So yeah, my name is Luca Della Libera, and I'm a PhD student under Mirko's supervision at Concordia University. So for this project, I developed together with my colleagues Pune, Salah, Mirko, and Sam this benchmark for continual learning in ASR, multilingual ASR. So basically, continual learning is the problem of learning tasks continuously. And this is not trivial because when you try to learn tasks in a sequence, there is a phenomenon called catastrophic forgetting, which means that the model tends to forget all the knowledge acquired in the old tasks. So continual learning tackles this problem. And there is a lot of research for continual learning in vision and natural language processing domains, but we found a lot of research in speech processing. So that's why we proposed this benchmark. So in this benchmark, we identify a group of base languages which are well supported by current multilingual ASR systems. So these languages are English, Chinese, German, Spanish, Russian, French, Portuguese, Japanese, Turkish, and Polish. We pre-trained a base ASR model on these languages. And then we incrementally add new languages. So the one that you see here, so Kinyarwanda, Esperanto, and so on. So these languages are currently not very well supported by multilingual ASR systems. And typically they are low resource languages. So the challenge is to add these languages without degrading the performance on the base languages. So we provide different, in our benchmark, we implemented several methods for continual learning, including rehearsal-based, architecture-based, and regularization-based, and also several evaluation metrics to understand how well the model learns the new languages and how much it forgets the old one. So more in detail, so Mirko, if you can move on to the next slide. Yeah, so far, this is an ongoing effort. So far, we have implemented our benchmark on using the Common Voice 13 datasets. And we recently added the first dataset, so from which we extract these two groups of languages. And we currently support 10 continual learning methods, naive fine-tuning, then 3 real-star-based methods, 3 architecture-based ones, and 3 regularization-based ones. So including popular ones such as experience replay and progressive neural networks. As a base models, we have so far Whisper, both the tiny and large version, and WaveLM plus a CTC head, so that we can cover both the cases of weakly supervised and self-supervised. And we provide these 4 metrics that you see here. The most important are the average word error rate across all the tasks and the backward transfer. And we also provide scripts to automatically analyze the experimental results and generate plots as the one that you see here to easily compare all these methods. Yeah, so as I said, it's an ongoing effort and we're actively extending it. And we will also soon make a paper available which describes our framework. Thanks.
Thank you, Luca. So maybe it's time now to say a few more words about the self-supervised learning benchmark. Salah, switch on the microphone and can describe it.
Thank you, Mirko. Do you hear me well?
Yeah.
Yes, hello everybody. I'm Salah Zayem. Yeah, and we've been working lately on maybe what we think can be an improvement in benchmarking self-supervised models. So I'll start with a few motivations. So I guess a lot of people here, and we've seen that in the presentations, have been using lately self-supervised representations, and it's being used by more and more practitioners in the community and on even more tasks than what they were first trained for. So we really need, in this case, a proper benchmarking. You have, if you've been working with those models, you may have heard before about the super benchmark, which is the main benchmark in the field for self-supervised representations. So lately we've been working a little bit on that benchmark, and we identified flaws in the way this benchmark works. So we've discussed this in 2 papers we've released lately. One that has been presented the last week in Interspeech in Dublin. So mainly the main flaw is that there's a high dependency on the chosen probing head. So if you want to probe those representations for emotion recognition, the super benchmark will use a linear probing head. And we've seen that if you change the probing head to something sometimes more interesting or a little bit more complex, then you would have completely different rankings and relative performances. So those benchmarks are not resilient at all to any change in the probing heads. So this is why we proposed afterwards MP3S. So this benchmark, MP3S, stands for multi-probe speech self-supervision benchmark. And let's go to the next slide to know more about it. So it's pretty simple idea. We have a set of tasks. Those tasks are not limited to ASR, but we'll have speaker-related tasks, semantic tasks, intent classification tasks, emotion recognition tasks, and so on. And we won't consider only one probing head per task like in the super benchmark, but we implemented multiple probing heads for every task. And we encourage people in the community to actually either add tasks in the benchmark if they consider that their task is interesting and can gain from using self-supervised models, or even add probing heads if they think that they can propose downstream architectures. That's what I call probing heads, if you are not understanding. Downstream architecture that can exploit in the best way those self-supervised representation. And just to give you an idea about what I was talking on, I put on those figures on the right. So for instance, for emotion recognition, you have the first downstream head that is linear probing, that is the superb approach. We replaced it, for instance, with an ICAPA-TDNN-based downstream head, and you can see that the differences change a lot. And one of the things we observed is that base models, so smaller versions of those models, are generally gain a lot from using a little bit more complex probing heads. So here you can see that large models were performing better than base models with the first downstream head, but that's not the case anymore. 3 out of 4 for base models actually perform better than their large counterparts in the second part. And this is only one of the flows that we've discovered. More details can be found in the second paper that I've shown in the previous slide. We have different flows from efficiency, performance, advantage oversized models, or even the use of the layers in the model. So this is why we put on this MP3S. We hope the community will like it and maybe propose, as I said, other tasks or other probing heads. Thank you. That's all for me.
Thank you, Salah. Then the last benchmark that we are preparing is also pretty interesting. Like we are combining SpeechBrain with Moab, and we created this SP Moab benchmark, where essentially people can just like can be used, right, to easily benchmark EEG model. Like we have a set of like task, and you can just plug your model into this like our framework and see how this model compares with the others. This was a little bit missing in the EEG literature, especially because we are also releasing the toolkit with that kind of pretty solid evaluation protocol that ensures as much as possible that the comparison across different models is pretty fair. So in terms of, we have a diverse set of model and tasks. Specifically, we at the moment, we have a bunch of popular EEG models, which are evaluated on 11 datasets on tasks like motor imagery, P300, and SSVP, which are tasks very popular in the EEG community. And as mentioned, like we are not just releasing a set of recipes, but we are also releasing some kind of an experimental protocol that ensures as much as possible that the comparison across different models is done in a fair way. So we will finalize the pull request pretty soon. Maybe we'll write a paper as well. This is a collaboration that is going on with the University of Bologna and my colleague Davide Borra, and I hope it will be you will see the results of this big effort soon available in SpeechBrain. This is just to say that we prove here that SpeechBrain is not really just a speech toolkit. You can really use it for sequence processing task and EEG. We didn't have to modify any core functionality of SpeechBrain to support EEG. We just had to implement the EEG models and do this interface with Moab that is providing the pre-processed dataset for this task. That's it essentially. So SpeechBrain can be used for many signal sequence processing tasks, and that's a proof of that. Okay, so maybe we can move on. Unless you have questions, I hope you can write the question in the chat, and maybe Luca and Salah can reply. We can move on actually with another addition, which are like we implemented all the necessary steps for diffusion models, and I hope Artem is here and can mention what has been done to support diffusion.
I just gave access. You should be able to.
Okay. So Artem, feel free to start.
Hello, my name is Artem, and I'm a master's student with Mirko at the University of Montreal and Mila, and I'll be talking about diffusion. Other than ChatGPT and everyone being afraid of ChatGPT taking over the world, what's making the news in AI these days? Generative models. There's a lot of interest in being able to generate images from speech, or rather images from text, to generate entire videos from text, and also to modify a video, edit a video, which means making a modification to the original one, but generating a new one. So any kind of generative model. And this diffusion method is relatively new. It's been around for a couple of years, but it proposes a radically new way to generate samples. And the implementation we have in SpeechBrain is general. It's not dependent on any given task. What is diffusion? How does it work? Michelangelo said that if you have a stone, you have a statue already in it, you just have to remove all the extra parts. That's the essence. With diffusion, the idea is that during training, you add noise to your sample, and you're training a model to predict just the noise, which can then be removed. Now, during inference, what you do is you start with pure noise, nothing but noise, and there's a sample in it if you remove the extra parts. So one step at a time, you predict the noise, remove the noise, predict remove the noise, remove the noise until you recover a generated sample. Now, this generation can be unconditioned, which means just sampling from a broad distribution of data, generating an image, any image, or it can be conditioned. So text to images, text to spectrograms, anything like that. And more it's being used for speech. A task like TTS, text to speech, can be thought of as a generative task of generating speech conditioned on text. Now, next slide, please. To use diffusion on a brand new task, this is the type of model you would need to build. You would need to build a model that takes a noisy sample and then a time step embedding, which is just an indicator of how much noise has been added. And during training, you just sample. You add a little bit of noise, a lot of noise. It's just sampling from, say, a uniform distribution of the steps, and then it learns to predict that noise. And then during inference, you just do it one step at a time. And there's more advanced methods available that reduce the number of steps. But now in SpeechBrain, we have the basic diffusion that goes through all the steps. Now, next slide, please. Here's an example of how you can set up diffusion in your recipe. First, you create a model, and we do provide a sample model, which is a slightly modified OpenAI unit, which is used for image generation. But if it can be used to generate images, it can also be used to generate spectrograms that you can pass through a vocoder to generate speech. And here you plug in your model into the diffusion implementation that's already available in SpeechBrain, and you specify how many time steps, what noise function to use, and then some sampling parameters, and that's pretty much it. It already provides a way to obtain a training sample, and it provides an inference method. You just need to provide a model, and a sample model is available. Next slide, please. We also created a proof of concept recipe that performs generation on a very basic speech task, which is generating samples from audio MNIST. It's similar to the MNIST everyone has heard of, that's used for benchmark tasks and in all AI classes, but instead of digits being visual, it's someone saying digits. But this is a fairly large data set, lots of accents, lots of speakers, but all saying digits. And we have examples that are unconditioned. We're having examples that are conditioned on the speaker or on the digit. Here are a few examples. Mirko, can you play some of them?
Sure. Oh, wait.
Sorry.
Zero. Do you hear it?
Yeah.
Okay, so that's zero, right?
Yeah.
Conditioned on digit for zero. And this is one condition on one, like
one. Yeah, you see that the speaker changes because it's only conditioned on the digit here. And here it's conditioned on the speaker, the same speaker, different digits.
Okay. One.
unlike with the other example, it's the speaker it's the digit that changes, but the voice stays the same. Now, in this case, this is a very simple embedding because it's a discrete category, both the digit and the speaker. But if you want to condition your model on a sequence, you might need a more complex model, usually using techniques like cross attention or spatial transformers. There's a variety of others available, but the key point is that this is just a proof of concept. You can plug in any model in it, either using the UNet, customizing the UNet, or using something else entirely. Next slide, please. We also provide an implementation of latent diffusion, which is used for a variety of image generation tasks and image to text. Stable diffusion is probably the most famous one. The idea here is that instead of having diffusion operate in the sample space, which in the case of an image or a spectrogram is the raw pixel space, you train a big autoencoder for dimensionality reduction. Now, already this UNet that we use is very heavy, but if you want photorealistic images or large speech samples, you might want to reduce your dimension, because the diffusion already you might have to go through hundreds or thousands of steps at inference time. Now, if you use latent diffusion, you still have to go through the steps, but it takes a lot less time per step. Now, we do have a sample on AudioMNIST. Actually, on AudioMNIST, you don't benefit from having an autoencoder, because the reconstructions from an autoencoder would typically be blurry unless you train it on a massive data set, at least a vanilla autoencoder. But with large big data sets, you have the advantage of being able to train your autoencoder on a ton of data. In the case of these the state-of-the-art image generators, they're trained on half the internet, and then you train your diffusion only on a smaller data set, and you run your diffusion in the sample space, and it's the decoder that takes care of making your image photorealistic or making it high quality audio. And that summarizes diffusion. We provide the building blocks for any kind of diffusion model. Very simple examples to get started, and the next use of diffusion for the next state-of-the-art generative model that will make some bigger headlines is up to you. And
thank you. I think we need yeah, that's very interesting. You did an amazing work, and I encourage all people to take a look at our diffusion technology, diffusion recipes. Thank you very much, Artem.
Thank you.
Unfortunately, we need to speed it up, so can now talk about the use of speech synthesis. Let's try to maybe speed up a little bit if you can. So I guess it's Yingzi now, right, that would like to talk about text to speech.
You just gave access.
Do you hear me?
Okay. Yeah, please.
Yeah, okay, nice. Yeah, I can go faster. Hi, I am Yingzi Wang. I'm a speech engineer at Zhangyi Lab in Paris, and with Pranya, we're going to show you some new updates of the SpeechBrain TTS. We're going to talk about the text-to-mail module, the vocoders, and the zero-shot multi-speaker TTS at last. In the previous release, we have already integrated an auto-regressive model. The most popular one is Tackletron 2. And then in the new release, we're going to include a no autoregressive model, and the most popular one is FastSpeech 2. And we have two versions of FastSpeech 2. We have the normal one and the one with internal alignment. And we can first listen to some samples, and then we look into the difference of these two versions.
Okay, that's Tackletron.
Yep.
Welcome to SpeechBrain. This is a test run with Tackletron.
FastSpeech 2.
Welcome to SpeechBrain. This is a test run with Fast Speech.
and a fast speech shoe with internal alignment.
Welcome to SpeechBrain. This is a test run with fast speech internal alignment.
Yeah, so as we can hear, they are all of very high quality. And I don't know if it's that obvious, but fast speech tool can better produce the processes. Yeah, and now we can look into the models. Yeah, and for in the left, we have the normal fast speech tool. And to train such a model, we need to first pass the audio text pair to a forced aligner, for example, the Montreal forced aligner. And then it generates the phoneme durations for training the duration predictor in fast speech tool. And in a word, the normal fast speech tool needs a teacher. However, in the right, we have the internal alignment version. Just as the name goes, we train an internal aligner to learn alignments. So we won't need to go to a forced aligner. Yeah, and we can see some points to note. The next slide, please, Miracle. Yeah, in fact, both fast speech 2 models, they need phonemes as inputs. So if you have text, you need to convert them into phonemes. So we're using our SpeechBrain G2P model, which is of state-of-the-art quality, and our fast speech 2 can better pronounce. And with the internal alignment, we can better align the punctuations, because sometimes a forced aligner, it doesn't provide alignments for punctuations. And the third one is we can do easy training when using custom data. So if you have your own data, you don't need to go to a fast aligner. You can do everything inside SpeechBrain. And the last one is high quality, as you just heard, and the flexibility is a very good attribute of fast speech too, because you can change a little bit the audio generated. If you want faster, slower, higher pitch, lower pitch, as you wish. Okay, then we're going to look into the vocoders. Yeah, we have the new one is DiffWave. DiffWave is a diffusion model for audio generation, and we can listen to the samples. We can't hear anything.
We cannot hear the audio.
This is a test run with fast speech and Diffusion. Diffwave. This is a test run with fast speech and Diffwave.
Yeah, as you can hear, the audio generated from Diffwave is also clear enough. Okay, and we can take a look into the usage of Diffwave. Yeah, it can do many things. It can do conditional generation and unconditional generation. And here it serves as a neural vocoder, takes a male spectrogram as a very strict condition. And also it can take, for example, a speaker ID, a digit ID as a weak condition. And also it can generate from nothing. And the content of the audio just totally depends on the random sampling. Okay, and then we see some points to note. It can do conditional generation and conditional generation. And for inference, we have fast sampling. Fast sampling is a tech we use for inference of the diffusion models. We don't need to go to pass all the steps one by one. We need only a few of them. So it's much faster, but with similar quality. Yeah, and then we'll see some future interests for TTS. We think of multi-speaker, multilingual, and emotional TTS. And personally, I'm very interested by a test audio project. And yeah, it can be very cool if we combined with LLM. So that's it. So if you have some expectations of the SpeechBrain TTS, you can just leave a message and we can talk about it. Thank you.
Thank you very much, Yunzi. And let me officially thank for your great contribution. You did really a great job.
Thanks.
Yeah. And maybe a last note, maybe Pradnya, if you can like move on with the zero-shot multi-speaker TTS very quickly, you can just say quickly what we are doing. Pradnya?
Should be able to activate. Pradnya, can you activate your voice?
Yes. Hello. Can you hear me?
Yeah.
Okay. Hi, everyone. I'm Pradnya. I'm a master's student at Concordia University, and I will be talking about zero-shot multi-speaker text-to-speech. It is easy to work with because of SpeechBrain. So Yes, what is zero-shot multi-speaker text-to-speech? This diagram gives us an idea. So we have two inputs here, some text and some reference speech. And the goal is to map this input text to some output synthesized speech with the voice characteristics of the speaker from this reference speech. Okay, so what does zero shot mean here? It means there should be no fine tuning for unknown speakers. So the known speakers here are the speakers the model has seen during training, and unknown speakers are the speakers at inference time. And it should work well for both these cases. So how do we create such a model? What we do is we take a single speaker model and adapt it with an additional input with speaker embedding to create a zero-shot multi-speaker TTS model. Could you please go to the next, click next? Thank you. So yeah, we tried some experiments, and at the moment, the best model we have is a zero-shot multi-speaker version of the Tacotron 2 model. And a very high-level view of Tacotron is that it's an encoder-decoder. It has an encoder-decoder architecture, and we use speaker embeddings after the encoder part. And yeah, that's the main idea. So now we can play some samples.
The rainbow is a division of white light into many beautiful colors. The rainbow is a division of white light into many beautiful colors.
Hopefully, it will come from someone on our side. Hopefully, it will come from someone on our side.
There were no proposals on the table. There were no proposals on the table.
At the time, he was a living legend. At the time, he was a living legend.
So as you can see, it's trying to preserve the speaker identity, but there's still some room for improvement in terms of speaker quality, speaker similarity, and overall quality. It's a work in progress. Hopefully, in the future, we'll have better samples soon. But for now, yeah, that's it for zero-shot multi-speaker text-to-speech. Thank you. Thank you.
Thank you, Pranya. So here it's pretty cool. I think we are doing pretty well, and we will release the model soon as we can like improve the quality a little bit. Okay, so let's see what happens. So it's now time to talk about speech-to-speech translation, and I think this will be presented by Ha, right?
Yes. Can you hear me?
Yeah.
So hello everyone. I'm Han Nguyen. I'm a postdoc. At LIA Avignon, and it's my pleasure to present to you this recipe about speech-to-speech. Before presenting this, I have to emphasize that this recipe is 100% contribution from Jarod Duret, my colleague at LIA. He's doing a PhD there. Unfortunately, he's on the train to go back from the InterSpeech workshop, so he cannot present to you. But hopefully he's on the chat, so he can maybe better answer your questions. So first of all, this recipe is based on the CVSS dataset. This is a dataset that has that's based on common voice and also co-voice. They have several language. They have speech from several languages and translated speech in English, synthesized speech in English, and also they also provide the target text in English. But we shall see that we don't need this target text for training our model. We only need this text in order to evaluate our model. Maybe you can play to audio to see how the data. Yeah.
La parole est à Monsieur Alain Ramadier pour soutenir l'amendement numéro 128.
So it's French, but the accent is very weird.
I shall give the floor to Mr. Alain Ramadier to support the amendment number 128.
Okay, so can you next? So based on this dataset, French to English, we developed this system which has 3 separate components which are trained separately. So first of all, we have the unit discovery component, which technically take the target speech in English. We feed it into a self-supervised learning model, for example, a Hubert one, which can produce the latent representation, which is then fed into the our Kamin component, which is then cluster the representation into sequence of speech unit. And we use this sequence of speech unit instead of text for training our second component, which is the speech to unit translation system, which actually encoder decoder architecture, which we can use again SSL model, for example, words effect as our speech encoder, and then we can add like this convolutional layer in order to adapt the length of the sequence before fitting them into the transformer decoder. And this transformer decoder will predict the unit sequence. And once we have this speak to unit translation system ready, we will feed the output of this system into another component, which is the unit to speech synthesizer, which learn to transform a sequence of unit speech into speech audio in the target language. Maybe you can play the example to see. Yeah.
La parole est à Monsieur Alain Ramadier pour soutenir l'amendement numéro 128.
The floor is open to Mr. Alain Ramadier to support amendment number 128.
Yeah, thank you. You can see that the quality of the prediction is quite good. Can you next? So with this system, we don't rely on text data. We train everything on speech data only, which is good because sometimes we don't have text between our language pair. And this can be, with this recipe, we provide everything, every script for doing French to English, but it can very easily extend to other language pair. And also we see that we use Hubert and weight effect here, but technically you can replace them with any pre-trained speech model available on Hugging Face. And our future interest is to do multi-speaker or multilingual. Specifically, we also interested in using pre-trained decoder, for example, Ambrot, to replace the transformer decoder we use here in the speech to unit translation. With this recipe, we also you can next year.
We are already late. If you can speed it up a little bit.
Yeah. Can you next to the final slide? So with this recipe, we also provide with you the pipeline to automatically evaluate this kind of system. So it's technically we can technically load a pre-trained ASR model in order to transcribe the synthesized speech outputted by our system, and we use the synthesized transcription to score the blue versus the target text provided on this data set. I think, yeah, thanks to SpeechBrain, this is possible. We can easily load different pre-trained components. I think that's it. You can.
Thank you, Jarod, for this work. I guess the pull request will be merged pretty soon, right?
Yes.
Very good, very good. All right. Maybe Sam, you can say a few words about interpretability now.
Yeah. So I'll go over quickly. I just have one slide, anyways. So this is something that I've been working on in my research lab, quite focused. So actually, Mirko, can you just like refresh the slides? You just like close, hit escape, and then open it again. Yeah. And then, yeah. So this is a work that Francesco Paisan contributed to. I want to acknowledge that. So basically, the idea is, so, you know, we work with neural networks, right? Who doesn't these days? And they are mostly black boxes, right? Like we don't really know why they make decisions, especially if they're working with a classification problem. We don't really know why they make the decisions that they make, right? So the idea here is to provide explanations as to why they make their decisions. And in the audio domain, so we merged the recipe in SpeechBrain for that, for environmental sound classification, not speech yet, but this will hopefully come also. So for instance, you have a cat meowing, but like there's background noise in the middle, and then like that if you give this to an explanation module, basically it should highlight kind of like why it's making the decision it's making. So for instance, Mirko, if you could play, yes, that one. We don't hear, so I think you have to unmute yourself.
Can you hear?
No, play again. No, we don't hear. Play another one, maybe. Should I share my screen?
Well, it was playing before, but if you would like to share your screen,
yeah,
feel free to do.
Because it's like pretty important.
I don't know what happened, but you know, before
Yeah,
the
maybe,
samples.
yeah, you can.
But feel free to share your screen, no problem.
One second, I have to post some stuff. Okay. Do you see my screen now?
Yeah.
All right. So I think I have to. Do you hear that? Did you hear that?
Nope.
You didn't hear that?
No, we can't.
No, Sam, what you can do is to copy and paste in the chat the page where we have this example, such that people can just like.
Yeah. Okay, it's fine. We'll do something, but the idea is it's kind of like source separation, but actually you want to highlight with a listenable explanation why the classification, original classification is model doing this decision. This is called post-hoc interpretability. And one thing I would like to announce is that in ICASP 2024, we will have accepted workshop on this, basically interpretability for speech and audio. The workshop, the link is here if you're interested, and that's it for me. I'm sorry that I couldn't share the audio. Yeah.
Please, Sam, share on the chat the page where we are.
Yes, I'll share the landing page where you
because it's pretty cool actually. So, but you know, let me move on with the very last part of this. Like, can you see my slides? Yeah. My screen, sorry. Yeah. Okay, so there is much more. Actually, we don't go in detail here. There is much more that we are doing. Like, we have Yinzi is here. He works also on a emotion dataset. Now we have like in speech recognition available a recipe for doing emotion diarization, which is like a pretty cool task. This is done with a new dataset called Zion Emotion Dataset, and you can refer to the repository for more information. And also we are writing a paper. We are going to, as I mentioned, we are going to like combine SpeechBrain with some kind of large language model. Like essentially, we are creating some recipes for fine-tuning large language models on SpeechBrain. We already have done that for GPT-2. There's a pull request that we are gonna merge, and the goal is to do that for Llama 2 pretty soon. So in the future, you will have the possibility to import a pre-trained large language model and fine-tune it on your own task. And that's pretty cool because, you know, if you do that, you can have the pipeline that can go from speech to a text all the way along. So there are other news. We are working on streamability as well. We have like, we are releasing a streamable VAD. And as mentioned before, we are also working on streamable ASR through a conformal transducer. We have a new recipe for speaker recognition based on ResNet, and also for speech enhancement. Now we are working on a new recipe for DNS, a new baseline for DNS. That's all. I hope we discuss about many things, right? We are doing an amazing work, and I hope you guys can take a look at the new version of SpeechBrain soon and share your feedback with us. That's it, I think. What we would like to do. We will do a virtual session.
Well, the break is after, so we can, I think, continue with Peter's talk now.
Okay.
We had the roadmap before, guys. No?
Yeah. Oh, yes. It's not the end, right? All right.
Well, no,
the roadmap is now. Like the roadmap is now,
yeah.
not at the end.
If you, Titman, sharing the roadmap, that's very important. Yeah.
Yep. Let me do it.
Forget about
it. Share. Okay. Should be good now, right? Hopefully. Yes? Okay. I'll be quick because we spent a lot of time presenting what is new in SpeechBrain, and what will be new in the future is also quite important, I think, so that you can see that we are not stopping here. SpeechBrain the version 1 is just the beginning, somehow we can say. So we will keep pushing SpeechBrain along 3 main axes. The first one is software engineering, the second one is scaling up, and the third one is scaling down. So basically in the first one, this means that we will try to focus on things that industrials are looking for. So this means, for instance, torch script compatibility to make sure that you have improved training speed, or better inference speed, or even easier exports when you want to put things into production. We'll improve the continuous integration as well. We would like to test the API from Hugging Face, not only the interfaces. Also test SpeechBrain against different torch versions, for instance. So basically just widen the number of tests that we do. We are also planning to work toward better industrial tools, as I said. So we'll provide very soon ONNX export tutorials. We will also provide streaming tutorials to show how we can actually build a real SpeechBrain demonstrator from the ground, right? Like, so starting from the speech up to what you are interested in. So it can be, I don't know, maybe you will need voice activity detection, then speech recognition, then you want to do some NLU on top of it, or whatever. We will try to give you tutorials to build a full pipeline in SpeechBrain so that you can showcase your systems. And we'll also work on stability, because we know that when you want to use, for instance, mixed precision, which is quite common, right? When you want to train big models, you end up with a lot of problems and issues that can happen. And so we'll try to fix this in the future. But this is a problem everyone has. It's not only SpeechBrain. Training with mixed precision can lead to issues. What do we want to go for in terms of scaling up? It's going with more efficient SSL pre-training, so like data to vec 2.0 or BestRQ. Other toolkits already have implementations of Hubert, for instance. That is not an efficient SSL method for training purposes. Our goal here is to enable the community to train themselves SSL models, large ones. And so to do this, you need efficient SSL methods like data2vec and BestRQ. So this is something we'll do. Then we also would like to work on something that we will call OpenSB, so for Open SpeechBrain, ASR and OpenSB speaker. So this is basically, the first one is a recipe to train a really large ASR model with all the openly available data. So you can think of this as a whisper, but one that is controlled, meaning that the community will be able to replicate the model, or at least look at the data preparation script and see, oh, everything is being done. What are the data sets? What are the evaluation metrics? What is everything in the SpeechBrain ideology, right? And we will do something quite similar, hopefully, for speaker as well, where we would like to build a better speaker embedding extractor, because right now SpeechBrain, the ICAPA-TDNN speaker embedding extractor that we have, is certainly one of the most used in the world. And this might change according to some internal sources. And so we would like it to not change, basically. And so we will try to soon train a much larger speaker embedding with all the available data again. So everything, again, transparency, documented, so that the community can reproduce. We wish also to reproduce Whisper. So we can't in terms of data, but at least the architecture and the way it is trained. Would like to have a recipe so that people can try to replicate a small model, for instance, of Whisper. And we will go with larger RNNT and CTC attention model with streaming ASR, because we know that this is very important for the industry. So this is like, we will put a strong focus on streaming and large-scale ASR streaming models. And of course, more recipes, more data set, more tasks, and we will be given priority to ASR, speaker verification, speech translation, and text-to-speech. By scaling down, what we mean is going the opposite direction, right? And this is also linked to industrial interest, but also research. So we'll very soon, hopefully, have recipes to show how to do model distillation. So we already have a recipe for distillation, but it's like from ensembles of models. Here we will really do model distillation for compression. So trying to compress very large SSL ASR system, for instance, or SSL models. And we will soon explore also post-training and training-aware quantization, so for faster inference. So this is, again, for a deployment under maybe constrained environment, or maybe not, if you just want faster inference. And also, in the end, all this is to hopefully deploy or propose a small footprint ASR model. So for now, it's ASR. Maybe it will be other speaker or other task model in the future. But as a first try, it will be for ASR. So we will propose a full recipe integrating all the above points to have a low latency and low memory footprint English ASR. So hopefully this will also be like a full tutorial with multiple recipes, so that you can see what is the pipeline to achieve this. So to conclude this part, so this whole part that we've talked about SpeechBrain, we couldn't conclude this with a brief recap and something that is quite important, I think, from this is like a message coming from the whole core team and all the people that collaborated on SpeechBrain. All of this is not magical, right? We really need the community. SpeechBrain is built and driven by the fact that the community is interested into it. Because with this, then we can maybe ask for money or help from sponsors, right? SpeechBrain version 1, so up to today, in 3.5 years, we only, I can say only, needed $200,000 to build SpeechBrain with all the people that talked, right? Because like this is quite efficient, I will say. So if you are enjoying SpeechBrain right now, this is not only thanks to the community, so yourselves and everyone and our work, but most importantly, this is thanks to our sponsors, right? I know it sounds a bit like marketing, but this is a reality. Without them, no SpeechBrain. So we don't need millions of dollars to build the next feature required by your institution or anyone. So if you're part of an institution, talk with your managers, or if you are the manager, help us, right? This is like reaching a lot of people. A lot of people are using SpeechBrain. You could be using SpeechBrain. And this is not magical, as I said. With this being said, I think I will just hand over to our next speaker. And thanks for your attention.
Thank you, Peter. So imagine what we did with $200,000. Imagine what we can do with more. So I think we are using really our money in a very efficient way. We pay excellent students to contribute to our toolkit. So I think the donations are actually well used, right? Definitely well used, as you can see in our toolkit.